So I will get out of the way and introduce Inka Milewski. And she is just a lovely individual. And I brought something downstairs to show you. When I started researching Inka, I realized that there was so much material on her. This is what I began with. And I finally stopped because I didn't want to kill any more trees, number one. But I realized what a prolific author this woman is and how well-spoken and well-versed she is in the subject, and which is definitely her passion. She is, as I said, a scientist, quintessential scientist. She's out in the field. This is not somebody who sits behind a computer. She's out in the water. She's out studying. And it's just fascinating to hear and see her videos online, read her blogs, and just see where she is on this whole subject of industrial aquaculture. She's a frequent contributor to the media and has testified before Maine authorities as well as Canadian authorities on the topic. So I will get out of the way and let Inka have the floor, and thank you so much for being here.
Too kind. Thank you. I thank you for the invitation to be here, and I'm just going to just do a little technical thing so I can get out of this and into my program. Great. The topic, dirty bottoms, this was something that was suggested by Becky after some considerable conversation around the work that I'm currently doing, some research around looking at the recovery of the bottoms under sea farms post-farming. So when a farm is decommissioned or is abandoned, I'm looking at how the bottom recovers, and I'm going to talk a little bit more about that later in the presentation. But what I'd like to do in this presentation this evening is to look at the history of salmon aquaculture in New Brunswick and Atlantic Canada. It's something that I know most about. I understand that there are some people here who are interested in shellfish aquaculture, and I can answer some questions around that as well, perhaps at the end of the lecture. So I'm going to look at the history of aquaculture, the rise of aquaculture in New Brunswick and Atlantic Canada. Then I'd like to look at some of the environmental issues that are associated with the industry, and then I'd like to look at the future. What is the future for the industry? So the story begins for me and the industry in St. Andrews. I actually came to St. Andrews in 1983, and I began working at the Huntsman Marine Science Center. But several years before that, in 1976, a scientist at the biological station, which is run by the Department of Fisheries and Oceans, called the St. Andrews Biological Station, there was a scientist there named Dr. Arnold Sutherland. And he, in 1976, was invited to take a sabbatical year in Norway. Dr. Sutherland had a specific specialization, or he was known to have expertise in, and that's salmon physiology. More specifically, understanding the process of salmon smoltifying or going through the smoltification process when they're moving from fresh water to salt water. Now, St. Andrews is also known for its other scientific institutions. The Atlantic Salmon Federation is there. We have the Huntsman Marine Science Center, and we have the St. Andrews Biological Station. So it really was a hub of scientific activity. So Dr. Sutherland in 1976 went to Norway, where the Norwegians were just beginning to develop salmon farming. They were raising about 2,000 tons of salmon a year. It's very modest, but certainly the country with the highest production. When Dr. Sutherland came back, he thought, we could try this in New Brunswick. And in 1978, the first smolt were put into cages in Deer Island, here in Lord's Cove. This is Deer Island. And they put in 3,500 smolts, and about a year and a half later, which is the time it took to grow out these salmon, they harvested the first farmed salmon in New Brunswick. And there was a lot of excitement that was generated because of the potential. Also at this time in the 70s, there were several things happening in the fisheries that gave regulators and gave people optimism that perhaps this was could be an alternative to an alternative activity for fishermen to do when perhaps other stocks were depleted and they were no longer able to be out there fishing. The wild salmon by the mid-70s were already in decline, the inner Bay of Fundy stocks. By 1985, they had actually they would impose a moratorium on commercial salmon fishing in the inner Bay of Fundy. So there were a lot of economic and social factors that went into giving biologists and regulators and policy people some optimism about this new thing called aquaculture. So the first site here, then a second site went in Ramanan, and it was quite successful. The price per pound for salmon at that time was about $7 a pound to the grower, which was really quite exceptional. So it was very profitable to be growing salmon. 10 years later, there were 52 farms licensed in New Brunswick. This is Passamaquoddy Bay. This is the Latang Inlet. This is Campobello Island. Salmon farming went from 52 farms. A decade later, in 2000, we went to 94 farms. Not only were the number of farms increasing, but the production per farm was also increasing. In the 1990s, they were probably raising per farm about 100 metric tons, maybe 150 metric tons. By 2000, they were up to 300 metric tons. So we're looking at going from raising back in 1980, putting about 7,000 fish per farm, to 2000 when we're raising about 200,000 fish per farm. And production, you could see in in 79, peaking right here at about 35,000 metric tons. Now, adjacent in Maine, of course, we had salmon farming taking place primarily in Cobscook Bay. At the peak of production in Cobscook Bay in 2000, there were about 28 farms in Cobscook Bay producing about 16,000, 17,000 metric tons of salmon. So this was not only had this phenomenon had spread beyond New Brunswick into Maine, but it was also a global phenomenon. This is global farm salmon versus wild salmon, and you can see by the mid-80s, the amount of farm salmon was starting to exceed the amount of actual wild salmon caught in a capture fishery. And today, and by 2000, the amount of salmon that was farmed far exceeded the amount of wild fish. And in fact, salmon was not only grown in places where it was indigenous, like Norway and eastern Canada, or northeast of the United States, but it was now being grown in countries like Australia, out on the west coast of BC and Oregon. It was also grown in Chile. So salmon, Atlantic salmon, was basically, they were dispersing the species in places that it really was not indigenous. Globally, the trend in aquaculture in general, it was not just farm salmon that was rising in production, but we also started to see a massive or increase in growing mollusks, primarily mussels, crustaceans, primarily shrimp. And in fact, the production in terms of aquaculture production globally is dominated not by farm salmon, it's dominated by freshwater species like tilapia and carps, and mollusks like shrimp and mussels. So those are the primary species that have fueled this incredible rise in interest in aquaculture production. And of course, this rise in the industry has also fueled a great deal of speculation about the role that aquaculture could play in feeding the hungry of the world, or meeting protein demands, or addressing the issues of depleted wild fisheries. We know that fish stocks are declining, that somehow aquaculture can meet those needs or demands, and aquaculture became sort of synonymous with what people call the Blue Revolution, that this was going to be, what was going to occur at sea was what had taken place, say, 50 years earlier on land, which was the Green Revolution. But as you can see, that the species that are being grown in the ocean are actually dominated not by a lot of different species, but the concentration of aquaculture on focusing on several key species. And that's exactly what's happened in the Green Revolution, that we're actually growing fewer number of species of plants, but we're growing them in very large industrial operations. And that's exactly what has happened in aquaculture. We've gone from little mom and pop operations to basically industrial feedlots. There are now salmon farms that are being proposed in Nova Scotia with 1 million fish per farm. And these are, so it's gone, it's also gone out of the hands of individual owner-operators into multinational corporations that operate these farms. As with any industrial feedlot, you have waste generated from it. What we see in the oceans, of course, is these open net pen systems. The cost of dealing with that waste is essentially not borne by the operator, but it's borne by the environment. When we ask ourselves, well, how much waste can a fish farm produce, we need to sort of look at just some of the basic inputs and outputs of fish. You need to have some feed. We can do some calculations on the waste production from an average salmon farm, an open net pen salmon farm, that produces roughly, an average farm today, maybe about 500 metric tons. And the estimate is that in order to produce that much fish, you need about 550 metric tons of feed. With that means that the conversion ratio is about one pound of fish, 1.1 pound of feed to produce 1 pound of fish. So we get the feed input in this would be about 550 metric tons. Now, there are three components to the waste. And by volume, the organic and dissolved waste are the biggest waste stream from a salmon farm. So you would get the estimate for the amount of waste feed that's not picked up by the fish is about 2.3% of the total input. So we're looking at about 12.6 tons of waste feed that is not picked up by the fish, that is deposited on the sea bottom. The estimate then for the amount of fecal waste that is produced is about 15% of the total feed that is eaten. So of course, not all the feed gets turned into protein and growth, that there has to be some feed waste. So we're looking at about 82.5, 80 metric tons for every 500 metric tons of fish produced. So a combined total here of close to 100 metric tons of waste, solid organic waste, from a farm producing about 500 metric tons. You still have the dissolved nitrogen component of that, and that is about 16 metric tons. So we're looking at about 32 grams of nitrogen per kilogram of growth, and that estimate comes out to about 16. So there is, as you can see, a considerable amount of waste that is released from a salmon farm in an open net pen situation. And this is just one farm, and this is a modest farm of about 200,000 fish. So we're looking at farms that are now estimated to be producing a million fish. You can do the math yourself. This is a considerable amount of waste. Now, how does this stack up to perhaps other sources of waste that are being discharged into a particular bay or area? Well, and this is really quite remarkable. The only real number crunching that has been done on this is some work that was done by Peter Strain and Barry Hargrave, who were scientists at the Bedford Institute of Oceanography. They were DFO scientists. And what they did is they looked at the Latang Inlet, which is, it is known to be the area with the highest concentration of salmon farms in the world. It's a very small area, and it has, I think at the time that this work was done, there were something like 22 salmon farms in this particular small bay. And what they did is they calculated the amount of nitrogen from runoff, from precipitation, from the sewage plant, from the pulp mill, the cannery, and the fish plant. Now this bar indicates that they did two calculations. One was this long bar is before they actually put a treatment, a new treatment plant to deal with some of the waste. And when that was put in place, the amount of nitrogen actually was cut back considerably. But the aquaculture input from all those farms was significantly higher than the combination of all of these sources. And this biological oxygen demand is a function of how much organic material you have in the water. And you can see here as well that the amount of the biological oxygen demand from the aquaculture operations far exceeds the amount of inputs from all of these other sources. So the contribution of organic and dissolved waste from salmon farms can be quite considerable, singly, but also in combination. And this is something that needs to be looked at in terms of looking at cumulative effects. And so what is the impact from all of this organic waste that is falling out and depositing on the bottom? Now, of course, the amount that's deposited on the bottom depends on several factors. The strength of the bottom currents that might disperse the waste. It's also a function of how the feeding regime, the number of fish on the farm. There are lots of factors that affect what happens. But what we do know is as the organic waste is loaded, there's a predictable response to the biological community, in the sediments, as the waste accumulates. There's not only a biological response, but there's also a chemical response. And this is some work that has been known since the 70s This is the Pearson and Rosenberg's work. And this response is that as you load organic material, the oxygen demand in the sediments begins to decrease. Well, it increases, but as it increases, the bacteria in the sediments begin to shift and change because they're responding to a low oxygen environment. There's more CO2 being produced. That bacteria that species has to shift because it has to live in a low oxygen environment. That bacteria, in turn, it produces sulfur because it's taking the carbon, it's utilizing the CO2, and it's producing sulfur. And if you go far enough down as the sulfur increases, that ultimately the bacterial species changes, and you get bacteria that are producing methane, not the sulfur. So you go from bacteria producing CO2 to bacteria producing sulfur to bacteria producing methane. And of course, as you move along this, the number of species that can actually live in these high sulfur, low oxygen, high carb CO2 environments shifts as well. And so this Pearson and Rosenberg defined this transition. They called it a normal zone where you have these dominant species. You have a transitory where the bacteria and the chemistry is sort of in flux. You actually get a little bit more species because you've got more organic material, which attracts more. But then as you shift over to this sulfur and methane producing bacteria, you get very few species, and it's dominated by a worm called Capitella. And when it gets grossly polluted, you actually get no macrofauna you get no species in the sediment, but the sediment is covered in a kind of a white bacterial blanket. And this is, you can see this visually. Over here on the left, you have a normal, it's called a normal sediment environment. There's a quality to the sediment that it's a little fluffier, it's lighter color, but as you begin to load more organic material, you start getting these patches of bacterial mats called Begiatoa or Begiatoa species. And as you get to a grossly highly polluted environment, these mats become extremely extensive, and it's almost like wet Kleenex sitting on the bottom of the sediments, on top of the sediments. And it's highly toxic, and very often you get sulfide gases outgassing from the sediment, and ultimately methane. And it really is essentially a bit of a dead zone. How big is the footprint of these the organic waste that's deposited under sea farms? This is some work of Blythe Chang and Fred Page at the biological station, and what they did is they looked at several sites and increased the number of sampling sites around these farms to try to get a picture on what the footprint of the sulfides in the sediments are around certain farms under different growing conditions and in different water depths and current speeds. And you can see that in blue are fairly what are called normal, 0 to 750 micrograms per molar of sulfides. This would be considered background or normal. Anything from light blue to red indicates elevated levels, with the red being sulfides of over 6,000 micromolars, which is very anoxic. Lots of outgassing occurring. Now, the fact that this light blue could actually stretch further out, but it was this is within the realm of their sampling regime. So if they had sampled further out, they might have found that this footprint was much larger. But even that said, in some areas, the amount of area affected by the organic loading was anywhere between 6 to 15 acres. So it's a considerable part of the sea bottom that can be affected by the organic loading, and it can stretch beyond the 100 or 150 meters that is suggested that the organic loading has an impact. And these are some different scenarios, different configurations of cages, salmon cages, and sampling programs that the government has, certainly in New Brunswick, requires that a farm like this would only have to sample at about 4 locations. And it's very difficult, based on just those 4 sampling points, to determine what the impact would be of the salmon farm. So what are the impacts from the dissolved nutrients? What happens, of course, is the nutrients are absorbed by some of the algal species. This is a bloom of green algae, an opportunistic annual algae. People call it sea lettuce or alba, growing next to a salmon farm, which would be not unusual. It's that influx of nutrients that is quickly taken up by these opportunistic species. Now, this is growing over top of a bed of rockweed. And if it's persistent enough, if this bed of seaweed is persistent enough over a long period of time, and it accumulates, the rockweed underneath that would basically would become anoxic, and it would perhaps die off. And that's a problem. They've found that some clam diggers have also found that these beds of algae are sitting on clam beds, that the clams under the beds, under these algae are smothered or the conditions become anoxic and they're killed. They also have, there are also blooms of brown algae, what people call brown slime. So people refer to this as green slime and brown slime. And this occurs in response to heightened nutrients in the water. So you get a shift in species that is dominated by these fast-growing opportunistic algae. There can be an increase in toxic algal blooms, phytoplankton blooms. You can get localized oxygen depletions as a result of the amount of nitrogen in the water, which is causing the growth of these algal species, which decompose, which eat up the oxygen in the water, and you can get these localized dead zones. You can get shifts. If this persists long enough, you can get shifts in species. You can have fewer filter feeders, and you can actually go to more worms, because the sediments are becoming, or the sediments are becoming more anoxic, and you don't have as many, the mussels are just unable to deal with all the material that's in the water column, and this is all settling out, and it's populated by worms as opposed to clams and mussels. And you can also get increased diseases in fish, crabs, and or lobsters. That's also something that happens or is associated with these nitrogen blooms. Now, everyone would say that nutrients in the water, well, that's natural. Organic material in the water, well, that's natural. And that these impacts that we see under salmon farms, well, you just give it some time and things will recover. I had an opportunity in 2000 to begin to look at what is the recovery of those sediments under a farm, a fish farm. how quickly will those sediments move from being anoxic or quite high in their sulfides to being like background, like they were pre-farming. This opportunity presented itself. It was the first, and it's interesting, but this is the first study of its kind in New Brunswick that's been done. Even though we've had all of these salmon farms, that no one has actually looked at how long does it take for the sediments to recover. Now, the industry has suggested that the fallowing period, allowing fish to sort of those farm sites to rest for 2 months or 6 months is sufficient to allow the sediments to recover. So we wanted to test that theory or that assumption that 2 months or 6 months would be adequate to have the sediments recover. So this was a fish farm that was the Pearl Harbor Penn Island fish farm. Was a license that was given to the grower because there had been disease outbreaks and the farms were going to bay management and to year class separation. So this was a bit of a kind of an emergency license. About 295,000 fish went into the farm here in July of 2000. 18 months later, in April, they began to harvest those fish, and the last harvest took place in August of 2002. The fish farm license was not renewed because they found that when they had been monitoring the sediments for the chemistry, the sulfide levels were actually very high. It had only been there for 18 months, and yet the sulfides had already began to build up in the sediments. So I chose a control site about 200 or 300 meters from the farm, and I began the survey, and I resampled for the next 3 years. And what we found was that these are the sediment samples from the farm site, the former farm site. This was our reference site. And we found that in the first year, the reference site had 31 in terms of species, in terms of the diversity of animals living in this sediment. There were 31 different species. In the farm site, there were just 10. So there was 3 times more living in these sediments than there were in the fish farm, former fish farm site. The following year, we saw a slight decrease, statistically not significant, but we also just saw a very slight increase in the former fish farm. So a year later, while the sediment chemistry was very quick to recover, we went from sulfide readings of 1,500 micromolars of sulfide down to about 800. The species were lagging behind the recovery of the sediments in terms of their chemistry. And in the third year, we still did not have recovery to our reference site. So 2 years on, and the sediments had still not recovered completely. And this was a farm that was in operation for only 18 months. The work I'm doing this year, or starting last year, is a farm site in Shelburne Harbor. You may have heard about this farm, Shelburne Harbor, because it's made the news recently. There's an outbreak of infectious salmon anemia on one of the farm sites in Shelburne Harbor. There are 3 farm sites in Shelburne Harbor, and this Sandy Point site is a farm site that began operating in '91, but in 2011 it was vacated because it had very high sulfide levels. Now, it was relocated from its existing site to about 200 meters north of the existing site. But but this is not the farm that has the ISA in it. I believe it's not. So what I did is so this opportunity presented itself to do another study on a farm that had been in operation for a much longer period of time, 20 years. So this is some of the monitoring data from the provincial government to look at what sulfide levels, which are monitored every year at the farm site. But the data we have only goes back to 2004, and you can see that over the years, the sulfide levels have indeed crept up to well up into anoxic levels. And then it dropped, and then it was fallowed for a year. And you can see that the sulfide levels do recover quite quickly. Still high, but the farm went back into production, and just as quickly the sulfide levels began to creep up again. So even in this instance, a year of fallowing certainly dropped the sulfides, but the sulfides are coming back up again. So I want to look at, we know what the chemistry is doing, but what is the biological community doing? How is it responding to the fallowing? So this is our sampling site. This is the farm lease area. These are SH1 is this refers to a video transect. This refers to a second video transect that we took, and this is my control site over here, and we took a video transect. And these are also our sampling locations for sulfides, organic content, and a variety of other geochemistry that we're doing. This is the grab sampler that we used. We did the samples on board. We had a live video camera feed. This is my assistant Adam, who's helping me deploy the sampling, the camera that we used. And here's what the sediment looks like under. This is not under the farm, but this is my control site. You can see the holes that are the holes of animals that are living in the sediments, some tracks of animals. As we move closer to the farm site, we start to see these mats of Vegeatoa, just tiny little bits of it. And as we move under the farm site, we see that the amount of these bacterial mats cover a significant part of the bottom. This is just a shot that is taken a little bit higher in the water column, so you can get a sense that we're looking at about 85–90% coverage of the bottom around the farm site that is covered in these bacterial mats. We also found, we also have photographs which show there's some uneaten food still lying on the bottom around these farm sites. And what we found in terms of species abundance and diversity, this is our control site, and we found that there were 16 species, 134 individuals. One species accounted for 65% of all the animals in that sample. So this would be a sample about the size of a small margarine container. In our in our farm site, we had 7 species, almost 600 individuals, and 2 species accounted for 91% of the individuals. And that's the Capitella worm, which is, there were 325 worms of that species in that sample. And the Capitella, again, is just one of those indicator species of a highly polluted environment. And here's a picture of it right here on the corner. So that's what I plan to do with that, is to sample again this year and the following year, and to continue sampling to see whether we will get, how long it will take for the sediment in fauna, or the biodiversity of that area of the farm, to recover to my control site. Now, fishermen who have been on the water, who are on the water, through this whole period of aquaculture expansion, have made observations about the impacts that they see on their fisheries and on the habitat that their fisheries depend on. And remarkably, that information has not been gathered in any effective way until very recently. Melanie Weiber from the University of Brunswick, Sheena Young, who's with the Fisherman Fundy North Fishermen's Association, and Lizette Wilson from Dalhousie University began a project to document fishermen's experience and their observations on fisheries aquaculture interactions. And they recently published this paper in the Journal of Human Ecology, and they identify what fishermen identify as the environmental impacts in terms of the degradation to the environment. These are fishermen who are setting traps or setting nets, that their nets and traps come up and they observe a smell that maybe is coming off of the sediments. So they kind of notice the sewage or rotten egg smell around fish farms, that they say that the bottom is sort of white or moldy or mildew or whitish. They notice that there's been shifts in their bottom type from sort of hard gravel to perhaps it's become very loose and muddy because the waste, the organic material is starting to build up beyond the farm area. They've seen a decline in kelp and rockweed. And of course, this is something that could be a function of nutrient loading as well as organic loading. They noticed that there are more starfish blooms around some of the farms. They noticed that the whales are no longer feeding inshore because a lot of these farms are located in, well, they are all located in coastal areas that producing some noise from maybe the feeders or there's lights, and that the whales aren't coming in. They don't see krill washing up on the beaches like they used to, and the herring aren't coming inshore. As far as the impacts they see on their commercial species like lobster, I mean, we do know that there have been lobster kills reported as a result of illegal pesticide use. The herring, they think, is affected by the light and the odor. They would say that the smell of the feed is a deterrent to the herring. They say that in scallops that they catch near fish farms that the meat to shell ratio is lower in the scallops caught around the fish farms. They notice that the sea urchin harvesters, their divers, they find that the shells are more brittle. The roe is discolored near the farms, and they have also observed dead crabs and shrimp. They found these near pesticide treatment areas or near the well boats. So these are some observations that the industry says they're simply anecdotal, but it certainly bears further scientific scrutiny and scientific work to confirm or dispel these observations. But these are fishermen who have spent a lifetime on the water. It's reasonable to look at their observations with and not be skeptical about them because it does come from experience. I'm going to just play you a very quick video. Last summer, there was a Canadian, it was called the Canadian Community University Research Association. This is a new group of university researchers who are working with community groups to do certain kinds of science. They had a meeting in Halifax last year, and they hosted, this is where Melanie Weiber presented her results. They actually had what's called a kitchen party in Port Mattoon, which is an area that is also being studied for its impact. There used to be a salmon farm in that area. The salmon farm is now gone. There are some citizen science going on. There's a collaboration between the citizens and the university to look at doing what I did in Pearl Harbor and now doing Shelburne. So there is this growing interest in citizens in communities doing science. But this is Clyde Fisher, who is a fisherman, a former master fisherman, talking about his experience with salmon farms and his fishery. So if we could just.
We were talking about this over on TV next, and down in Iowa, and they were just bringing this was like 2 days after the approval of the licenses in St. Mary's Bay, they were already moving the things in.
Right.
And there was so much misinformation down there that had been set by folks.
Right.
Obviously, about how good the lobstering is when you set your traps near the cages, all of that.
That's work. That works for 2 years at the most. And then it's down on the rest of the way.
Okay.
Right. So they use this year.
Person escape, but after a while they start to pull.
A lobster's got a great smell.
Yeah.
And a lobster, once a lobster, the bottom is free. A lobster will crawl over that bottom and go around it. I'll give you now this is something I do know, sure how it works. We've fished the lobster, and I've fished a lot. The last 20 years I went fishing. So me and the skipper, we always try to read the harbor because, and the way lobsters come, you try to read them, you try to follow them, try to get an idea of how they're coming in so you can catch lobster. So they have a system when they come in. They come in spawn, well, they have to let the eggs and stuff go and shape in the summertime. So they have a way of coming in. They always come up 3. They start outside and they'll come up 3. And then they come up around where the fish pond was. For the first 2 years, it was pretty good lobster man. But the 3rd year, they stopped. They wouldn't go up to it. And then it kept getting worse. So everything ended up at one bunch, and you had 8 or 10 boats fishing where usually one person fishes. And the 4th year, everything went around to get up to the ground. Yeah. After 5 years, nothing would come up. So, yeah, it's good lobster in the first years. And this is where they get this from. But they never ever tell you the rest of it.
That's in that library.
Yeah.
She said the lobster come right out to the farm. And they're projected.
Yes.
Yeah.
Yeah. See, we watched this.
This woman, Melanie Wyder, that's here. Yeah, she's written a paper, which she said is quite controversial. Because it's got a lot of reports from fishermen in it, a lot of knowledge from fishermen. And that's why I just skimmed it. One of the things I saw was lobster come up to the fishermen at the beginning. Because they probably like the extra nourishment.
Yeah, it's clean on the first study.
Yeah.
I'm interested in the dirty bottom because that's where also the other concept was, St. Mary's Bay is a dirty bottom anyway.
Yeah.
Is that true? So the lobster don't go in there?
No, they do have mud. It's not dirty. A dirty bottom is when nothing's dead, when everything's dead.
Okay.
Right? You can have a little mud on the bottom, might be that thick. But lobster can over that because there's a lot of food in front. Right? So that they got crabs and stuff in that. So they're feeding off of this stuff. But when it gets polluted, it's like a cloud. And underwater, if you touch it, it's like a cloud. And we got pictures of them that look like they're all round from the walking out with the smother. But so it's things like that. They just won't come. And it's like us, and we wouldn't be walking over the sewer system. around it. And they do the same. Their stones a lot better than ours. So, yes. So it's different.
St. Mary's is mostly a lot of data that have been lost. They don't quite know what was in, but they're using food of the unique rocks to hide food.
Yeah, so what they do, they come in over that mud building when they spawn. But if that one's smelly, and it's a change, and there's something changed in the ecosystem, they know it. So they won't go over it, they'll go around it, right? And this is where things change. It changes those. That's the start of the ecosystem changing again on the border. And that's just spreads. It just keeps spreading.
So that was Clyde Fisher talking about the pattern that they see when a fish farm comes in to their lobstering area. Beginning, first couple of years, the lobster do come near the farms, but after the sediment starts to build up with sulfides and it becomes really a sludgy and toxic. The lobsters don't come anywhere near the farm. I think it's pretty fair, to say that our oceans are in trouble. Rachel Carson wrote in 1961 that there's this belief that we've had that the oceans are limitless in their capacity to absorb the waste that we produce, and they're limitless in the amount that they can produce for us. But even in 1961, she came to understand that it was really quite naive on our part. This is some work that's done by my colleague, Feedlots from Dalhousie University, just basically describing the depletion of our ocean resources over time, over large cultural periods. Global 1 and Global 2 simply represent, these are cultural periods. This is from about 1900 to 1950, 1950 to the present. And this is where the steepest extinctions and depletions have taken place in virtually every category of marine life. The oxygen depleted areas in the world have increased dramatically. This is Robert Diaz's work, and he's updated this. This is 2000. He found that there were about 158 dead zones around the area, or oxygen depleted areas. He's updated that in 2007 in a paper in Nature. There are now over 400. So this is increasing exponentially. Eutrophication trends in your estuaries. This is Susanna Bricker's work at NOAA, where they've documented the eutrophication, which is the process of nutrient loading into our coastal waters, that the future trend is that things are going to get worse, and that the estuaries that are going to show improvement are decreasing. The source of nutrients, the rivers. Our rivers are discharging more nutrients into our coastal ecosystems. You can see that this is over time in the Northeast. It's 11-fold prior to the Industrial and Agricultural Revolution. I mean, these are a massive amount of nutrients that we're putting into our ocean. The other thing is our fossil fuel burning is resulting in nitrogen releases and NOxes into the atmosphere, which here is the deposition from the atmosphere, and these are occurring not only on land but also in our ocean areas as well. And you can see that through time, it's just simply getting worse. And now we've got a new source of nutrient and oxygen and organic loading into our marine waters, which is open net pen salmon farms. It's estimated that if NOAA proceeds with its sort of proposal to expand open net pen salmon farming in the U.S., that the amount of just simply dissolved nitrogen or nitrogen that could be released would be equivalent to about 17 million people. So we are dealing with an industrial source of waste that needs to be dealt with. And the thinking is that we can sort of, the technological fixes that have been pursued for aquaculture open net pen is to have these integrated multi-trophic sites, meaning if we just grew some mussels and some seaweed around these farms, we could absorb some of that waste and we could somehow reduce the impact on the environment. Well, you know, the science on that is still, you know, not in, because there are so many difficulties with that. The question is, how many mussel lines, or how big of that footprint of that farm will it get if you have to add so many more acres of mussels and so many more acres of seaweed to try to absorb some of these wastes, and that's just not happening. The whole question of whether salmon aquaculture is going to feed the world, the hungry of the world, or meet the protein demand of the world, the reality is that most of the world still gets, by far, the majority of its protein from vegetable sources and from animal sources. That fish and eggs, this is right down here, is a very tiny portion of our protein source. So it is really not necessary to have open net pen salmon farms to meet our protein demand. Our protein demand is being well met by all of our other sources. The other issue around aquaculture is that it's such an incredible source of jobs. But as you can see here in Norway, which is the largest salmon producer in the world, production of farm salmon has shown an upward trend, but the employment has shown a downward trend, because this is a classic case when you industrialize an industry as you do aquaculture. You put in place the technology that has efficiencies or improves efficiency, and when you do that, you actually reduce the labor costs. We certainly know that in New Brunswick, that the number of people employed in salmon aquaculture is less today than it was 20 years ago. Mechanization, underwater video cameras, this is work that can be done by fewer people, not more people. And right now, in terms of processing, the capacity, there are lots of fish processing plants that are idle, that it's not a question of building new processing plants, it's trying to make the best of an existing labor force. So we really don't need farmed open net pen salmon farms or farmed fish and open net pen salmon farms to meet any of our employment and food needs. In fact, for every one person employed in aquaculture, there's 4 to 5 people employed in the capture of wild fishery today. So there's a risk that some of the activities or the impacts associated with salmon farming could in fact have a greater impact on employment of the traditional fisheries. As I said, for every one job in the aquaculture industry, there's 4 to 5 jobs still in the wild fishery. What we need is, we need to talk about sustainable aquaculture. And it is aquaculture that really doesn't affect future generations, the use of the oceans by future generations, that it's aquaculture that the impacts or the waste that don't affect the ecological relationships in the ocean, that we're not putting chemicals and nutrients and creating a biological pollution, and that there's right now that there's no net loss of protein because we're still catching wild fish, grinding it up, and feeding it to salmon. There's a disconnect there, and it's not sustainable. One of the solutions that is being looked at is closed containment aquaculture, land-based closed containment. This is a very successful project run by the Atlantic Salmon Federation and a group out of West Virginia. They are growing quite successfully wild Atlantic salmon in closed containment systems. This is a picture from their operation in West Virginia. They've managed to capture 99% of all the waste that's produced in these tanks. They've grown these fish without the need for any kind of antibiotics and pesticides. They've had no disease outbreaks. It's really, we believe that this is the future of aquaculture, that it is an industry that takes responsibility for all the waste it produces, that it doesn't harm the traditional and wild fisheries that are out there, that in this case they're also experimenting with different feed types so that they are reducing the reliance on wild fish to feed these salmon. So we're really quite excited about the potential. Now the industry would say this is more expensive, it has a higher carbon footprint. My response to that is this is industry taking responsibility for its waste, not foisting that waste or that cost onto the environment. This is the true cost of producing a commodity that is largely being eaten by us very comfortable North Americans and Europeans. This is not producing a food that is being sent to sub-Saharan Africa to feed the starving of the world. If it's a luxury that we want, then I think we need to be paying for it. So, just to conclude, is we are really facing, given the state of the environment, we really are facing a challenge. Do we want an ocean environment, a coastal ecosystem that looks like this? Or do we want one that looks like that? I know what I would choose. I know what Rachel Carson would choose. We have the capacity to vote with our pocketbooks. We have our ballots, our voices to let our government legislators know that this is what we want. And we want aquaculture to develop far more sustainably than it's being proposed today. And we need to let them know that we don't want any further expansion of aquaculture, finfish aquaculture, and open net nets in our coastal waters. Thank you.